try a few more problems with empirical formulas. This first one, I'm given percent composition data, and I know that I want to use those percentages as grams. So by assuming a 100 gram sample, I could say that this compound is 54.09 grams of calcium. It's 43.18 grams of oxygen and 2.73 grams of hydrogen. Eventually, I need to find the mole ratio because moles represent a quantity of particles, and that'll help me piece together my formula. I can easily go from grams to moles. I just need my periodic table. So we're going to set these up to cancel grams. We want moles. 1 mole should have the mass on the periodic table. I'll do the same thing with every single one. Cancel grams, I want moles. 16 grams per mole for oxygen. Cancel grams, I want moles. Hydrogen is about 1.01 grams per mole. Now, again, this mole number that I have on my calculator is not necessarily my final answer, so I'm not going to be too picky on your sig figs, but leave something reasonable. I want to make sure that I have enough precision to get a good ratio. So maybe 350-ish moles of calcium. Ooh, I like this. About 2.7 moles of oxygen. Cool. Like 2.703 moles of hydrogen. Now these are not whole numbers and they're not close enough to round, but can you see the ratio? Yeah, I bet you can. This is probably going to be a ratio of 1 to 2 to 2. Now, if I wasn't sure, or if the moles came out to be kind of funky, then it would go through and divide each by the smallest. And then I know I get a 1, and it just so happens that these are pretty manageable numbers. 1.350. Now, this is kind of interesting. The way that you might want to write this formula, CaO2H2. However, the way that you'll see this on the answer key, calcium hydroxide. You could have done this problem without even doing a lick of calculations. Calcium is always in a group that's +2. That's going to be my positive metal in this ionic compound. Then there's always a negative, which is the nonmetals, and whenever you see 2 nonmetals, I would guarantee you it'll end up being a polyatomic ion. So if you see oxygen and hydrogen, it'll be hydroxide. If it would have been like sulfur and oxygen, I bet it's sulfate SO4. So they'll have it written in the formula as a polyatomic, hydroxide with the 2 on the outside. Now again, what I like about this one is that if I recognize that it's calcium, whose charge is always +2, and then if I recognized, oh, it's oxygen and hydrogen, I bet it'll be hydroxide. Hydroxide is always -1. You could figure out that there's 2 hydroxides just by writing the ionic formula. Well, that would have been a lot less work, huh? If you get lucky enough that the first metal is either a group 1 alkali metal or a group 2 alkaline earth, you kind of don't even need to do a calculation. You can figure out the formula by using their charges. Now that would not be the case with the second one. Now we want the empirical formula of a 0.0082 gram compound containing 0.0015 grams of nickel and 0.0067 grams of iodine. Awesome. Now, the one in your study guide may be written a little bit differently. And this is very similar to what we're going to do in the lab in a little bit. Later on in this chapter, we're going to take a copper oxide. We're going to decompose it in the lab. We'll be able to collect the metallic copper. Or in this case, maybe they collect the metallic nickel. But like in our compound, the oxygen will just be released to the surrounding air. Or here, like the iodine. Iodine can be a vapor. Maybe it's just released to the surrounding air. What you usually collect in the lab would be the solid metal. There's a couple like this in your homework too. We should be aware that the mass of the nickel plus the mass of the iodine should give me the overall mass of the compound. So if by chance I wouldn't be given, let's say, the iodine, but I knew the nickel, I could subtract them to figure out the mass of the iodine. Or in the lab, we'll know the mass of the copper oxide and we'll know the mass of the copper. If I subtract the two, I can get the mass of the oxygen. So the nickel plus the iodine should give me the mass of the compound, which they do. If I were to add these together, they do. Now, we have grams. They're super, super, super tiny. But it's okay. I can work with grams. This compound is 0.0015 grams of nickel and 0.0067 grams of iodine. Those are tiny numbers. Jeez. I can work with it. I want to switch grams to moles. Okay, so we'll set up our proportions. We'll cancel grams, put them in moles. On my periodic table, the molar mass of nickel, 58.69 grams. And then I want iodine in moles. The molar mass of iodine is 126.91. So let's see what we get when we plug these in our calculator. I mean, they're going to be ridiculously tiny. Yikes. So I get 0.00025556 maybe moles of nickel. And then let's do the second one, 0.0067 divided by 126.91. 0.005279 moles of iodine. Now, my calculator left them in a decimal form, but your calculator may have put these in scientific notation. So if by chance you have something that looks like, let's see, 2.556 times 10 to the negative fifth, that's totally fine. It's the same thing. Or this one might be 5.279 times 10 to the negative fifth. Totally fine. That mass, both of those masses are crazy, crazy, crazy tiny. We would not be able to measure masses quite that small in our laboratory. Now, at this point, you might have a hint at what this ratio will be, and if not, we'll treat it like any other problem and divide by the smallest. 0.02556, because I know that's giving me a 1. And then we'll do the same thing with the other one, 0.00005279. And if I plug this in my calculator, What do you know? I get it too. That was my guess. I was guessing that maybe it was twice as many moles of iodine. But again, if you have kind of crazy numbers, just plug it in. Divide them by the smallest. So here's my formula then. Nickel and 2 iodine. I2. If they ask me, what is the charge on the nickel, or what is the name of this compound? I know that iodine is always -1, so the nickel must have been +2. So that this compound is overall neutral. Nickel, 2 iodine would be the name of my formula. Cool. So after you do a few of these, there's some very similar patterns. You attack each problem the same way. If you have grams, great. Turn your masses into moles. If you have percentages, use them as grams. Assume a 100-gram sample. Get them into moles. This is very common in both of these, that you don't get whole number moles, but maybe you can figure out a way to make them whole numbers. Dividing by the smallest is always the first thing to try. If we would have gotten a ratio of like 1 to 2.5, then I could multiply them both by 2. Then we could make them whole numbers. So I would suggest maybe pause this, try the last one. The last problem is very straightforward on manganese. Give it a shot, bring it back, and see if you're getting these right. If you get this last problem right, you're in a really good place. Alright, so let's look at this last one. Hopefully you had a chance to try it. We have 2.5 grams of an unknown substance. They do give me the composition of the substance. Now again, they could have left one of these out. They could have said this is a compound of manganese, sulfur, and oxygen. I have 0.91 grams of manganese, 0.53 grams of sulfur, and the rest is oxygen. Well, if you know that the overall sample is 2.5 grams, you could just subtract to get the mass of the missing element. I believe there's a few like that in the homework. And again, it is similar to what we're doing in the lab. This one, I have all the masses. I can turn them into moles. They're small, but they're manageable. I can work with it. They're definitely not whole numbers. So we divide them each by the smallest. And often that'll fix it for you. We have a beautiful ratio, 1:1:4. And I kind of guessed that it was going to be sulfate. I see manganese, that's my metal. The metal is always the positive cation. And then ionic formulas always need a negative. Well, in this case, if I have 2 nonmetals, I bet it's a polyatomic, so that you get that 1 negative ion. The sulfur and the oxygen, it's probably SO4 sulfate. If it would have been like nitrogen and oxygen, I bet it's NO3 nitrate. And so again, if they would ask me, I could go backwards and I could write the name, I could write the charge on the manganese. That sulfate group is always -2. This whole group is -2. Since there's only one manganese, it must have been manganese +2. Or if I had to write the name, I would say manganese, Roman numeral 2, sulfate.